All right, here we go. Questions from 8.1, Foundations Math 20. Make sure you get your homework out here. Take a look at this. We did 1A yesterday. Compared the two rates. Let's talk about number 2. Compare the following situations. Determine the greater rate. So again, if they give you time first and liters of water second, like this, then the rate you'd normally do, minutes per liter, I guess. If you wanted to do liters per minute, that's also very good too. Like an amount of thing over time is also really, really good. So it doesn't really say, so you can do time per liter, that's fine. You're gonna have a pretty small number, I think. But whichever one you choose, you're just comparing the rates, so they don't give you much information other than that. So 4 hours and 50 minutes. We have to write 4 hours and 50 minutes either as hours or as minutes. Okay, not a combination of both. You have to just pick one unit. So if you did hours, you would use the number 4.25 because 15 minutes is 1/4 of an hour, right? If you have a clock on the wall, 15 minutes is exactly 1/4 of an hour. So 4.25 hours would work. I'm probably going to do minutes here because you might find it easier to convert this to minutes. So 4 hours would be 4 times 60 minutes and then plus 15. That's the total minutes here. So what's 4 times 60? That's 240. Plus 15 is 255. Okay? So you have 255 minutes for 300 liters of water. So you get your calculator out. And mine's coming, I think. Hello. Jello. Oh, here it comes. Maybe 2 of them popping up here, I'm not sure. There we go. Okay, we'll turn that on, clear it. So 255 divided by 300 is 0.85. So 0.85, that's minutes per liter. The second one, we'll do this in red. 2 hours and 10 minutes. Well, that's 2 times 60 plus 10, which is 130 minutes. Divided by, now how many liters of water does it take? 150 liters. So we do 130 divided by 150. All right, 130 divided by 150. What do you got there for a number? Anybody do that? Point what? 86? Okay, 0.86 minutes per liter. That's enough to tell us that this one is the greater rate, right? It's more. Well, does it say the greater rate? Yeah, greater rate. Well, this is more minutes per liter. Now, again, if you're talking about how many liters of water that a machine can process or something like that, then you're going to go liters per minute, and that's the greater rate, right? Like if you're pumping something out, it's a higher liters per minute. And that's easy. You would just flip these numbers around. If you wanted liters per minute, you would do 300 divided by 255, or you would do 150 divided by 130. That would be the liters per minute. Question?
So does it always not matter?
Well, it depends on the question which unit is on top usually. It doesn't really tell us here, so we're just taking the first one and dividing it by the second one. That's fine. Now, this one says so 2B says person A runs 400 meters in 1 minute 15 seconds. So we're gonna do meters per. Let's do seconds because it's easy to convert minutes to seconds. So 400. This is 400 meters divided by 1 minute is 60 seconds. So this is 75 seconds. So again, do that on your calculator. 400 divided by 75. So 5.333, and that's meters per second. The second person runs 1 kilometer. Well, again, we want to compare the same units if we're comparing rates. So that's going to be 1,000 meters. Remember that there's 1,000 meters in 1 kilometer. You guys do know that, right? You've seen that before. Hopefully you remember that. Okay. And then that's going to be in 5 minutes and 20 seconds. So 5 times 60 is 300, so that's going to be 320 seconds. You see that? And unless you actually divide these numbers and get to a unit rate, it's really tough to compare. So 1,000 divided by 320. 3.125 meters per second. So obviously this person runs faster. Okay? And it would make sense if this is actually two real people, because if you run 1 kilometer, you're running more than double this one, so you can't keep up the same pace for that long, right? So the rate would be a little bit lower for sure as you run a longer period. Okay, let's keep moving on. I'm going to do number 3 with you here, because this is a graph question, which I think is really important for us to understand what's going on here. So number 3, and again, nobody asked me about number 3, so I'm assuming you all did number 3 and you got it right. Or you haven't tried it yet. So hopefully you have. But number 3 says this: the graph to the left shows an ATV, how it travels over time. So this is distance on the vertical axis and time on the horizontal. Over which interval of time? So an interval of time means just a span of time. That's an interval. In math, we call those intervals. Intervals of x, or intervals of the domain, or intervals of time. So where is the ATV traveling the slowest? So that means it's covering the least amount of distance in a given time. Well, this slope right here represents the speed. So this slope is pretty high compared to this slope. This is a really steep slope, and this is a really steep slope. This right here is a flat part of the line. That means that the speed is 0 meters per, well, I don't know what this is. What is that?
About 7 seconds.
About 7 seconds. So if you look at the graph, the part of the graph with the smallest slope, okay, closest to 0, that's the where it's traveling the slowest. So I would say here that between 20 and, 20, that looks like maybe 28 though. So between 20 and 28 seconds is the slowest for A. Okay, slowest. And where's it going the fastest? Well, again, you want to see what's the greatest distance per time, or the steepest slope. And this looks like it'd be the steepest slope, because in his return to his starting point right here, this is the starting point. Now he's back at the starting point. He's 0 meters away from where he started from. He's covering 30 meters in, what's this going to be, 28 to 32 maybe. So 28 to 32 seconds is the fastest. Fastest, okay? When does the ATV start returning to its starting position? Well, it starts at this point, which is 30 meters away from its starting point, but more importantly at about 28 seconds. So B, at 28 seconds, it starts returning to its starting position. And then when does it get there? It gets to its returned starting position at about, we said this is about, looks like about 32 seconds. So at 32 seconds. Does that make sense? Okay. C, what does the 0 slope mean in the context of this graph? So C is stopped, not moving, right? Because in that time span, the person is covering 0 meters, right? They're going 0 up or down, 0 meters. So they are stopped. Any questions about 3? That's just a really quick one. Yeah.
I assume that on a test, we won't mark this down if like we have 27 and we'll blank 28 or something.
Okay, on a test, would I make a big deal of 27 or 28? Do you know what I would expect you to do? I would expect you to see that each of these squares is 5 seconds, okay? So I would expect you to look as closely as possible for this right here. This right here is, I would say pretty clearly, less than half of this span. You see that? So if you said this was 33, I would have a problem with that. Okay, if it was right in the middle, it would be 32 and a half. So it's clearly a little bit less than half. So your best guess would be 32. Yeah. So would I be really picky? I mean, come on, it's only a second. Like, it's not exact. I would expect you to be as accurate, as precise as the graph would allow you to. Okay? So yeah, I would expect you to look pretty closely. If you said this was 33 or 34 seconds, you would probably lose a half a mark there. Yeah, yeah, probably. I would have to say I would probably dock you a bit. If it's really hard to tell or impossible to tell, then I would have some grace. There would be a range of answers I would accept for sure. Yeah. Yeah.
Would you calculate that like using equipment to find the angle and came up with?
Okay, so this question doesn't ask you what the actual speed is, so you don't have to calculate the speed. But if you were to calculate the speed, it would be the slope of the line. So in this last interval, then it would be 30 meters. That would be the rise. 30 meters divided by, what did I say, 28 to 32? Divided by 4 seconds. So 30 divided by 4, that would be your speed, meters per second. But you don't have to do that for this one. Okay, one more. I thought number 7 maybe was a bit tricky, so I'll go over number 7 with you. So check your answers to number 7. But I'll go by it pretty quick here, though. So for each of the following, compare the 2 rates to determine the lower rate. So whole chickens, there's 2 rates. One is $3.61 per kilogram, and the other one is 10 pounds for $17.40. So in order to compare rates, we need to have the same units, right? The same units. So in blue, the whole chicken per kilogram, that's $3.61 per 1 kilogram. I would like to get the other one into the same units if I could. So I do have $17.40 per 10 pounds. So this 10 pounds is a problem. I want to convert that to kilograms. So guys, watch this. I did mention unit analysis the other day, and some of you I think are still a little fuzzy on that. But in order to convert one unit to another, one method that I love that is really helpful is called unit analysis, where we always multiply by some conversion factor that relates the unit that you're starting with to the unit that you want to end up with, in this case, kilograms. So if I arrange this so that I have pounds on the top here where I start, and on the bottom, if I multiply, those are going to cancel out. And so the relationship that I want to explore here is the kilograms to pounds relationship, okay? Now, the kilograms to pounds relationship, we know, is 2.2 pounds per 1 kilogram. So if you write it like this, which takes you 5 seconds, right, to write this, you can see that what you have to do to get kilograms is to multiply 10 times 1 divided by 2.2. So 10 times 1 divided by, divided by 2.2. Or just 10 divided by 2.2, because there's 2.2 pounds in a kilogram. So what's 10 divided by 2.2? Well, we'll figure that out real quick. That's going to be 4.55, let's say. 4.55. And that's going to be, kg. So guess what? This 10 pounds turns into 4.55 kg. You see that? So what is that right now? 4.55 kg. 17.40 divided by 4.55. 3.82. So this is $3.82 per 1 kilogram. So which one is the lower rate if you buy the price per kilogram? So this first one, right? This one. Okay. Everybody got that? Okay. I'm going to skip down to D. I'm not going to do all these for you. I want you to do some of these. So I'm going to skip down to D and do D for you here now. Again, unit analysis or converting rates, really important. So 30 meters per 1 second, or 100 kilometers per 1 hour. Okay? So I need to get both of these to the same units. Okay, girls, you listening? Okay, please pay attention to this. So I need to get these to the same units. Okay? Now it's easier to go from a larger unit, I'm just going to tell you, to a smaller unit, because then you multiply by something. Okay? So if I have a kilometer, that's a big unit, and I want to write this in terms of smaller units, meters, it's easier to go down to a smaller unit because you multiply. It's not that you can't go up to a bigger unit, but you'd have to divide then. So usually multiplying is a little bit more straightforward. So I am going to do this. Watch this. I'm going to convert, I'm going to do this down here, 100 kilometers per hour. And I want to convert that to meters per second. So watch this. This is where unit analysis works so slick. Because here, I'm not just converting kilometers to meters, but I'm also converting hours to seconds. So you have to do two conversions with one rate, and sometimes that can get confusing, but not with unit analysis. So I am going to multiply by something, and I just pick one. I want to get rid of kilometers, so I'm going to put kilometers down here, and I want to relate that to meters, and I know what the connection is between meters and kilometers. So if I do this unit, kilometers, is canceled out. Everyone see that? So I have 1,000 meters per 1 kilometer, so I write that down. And the beauty about unit analysis is you can keep multiplying as long as you want to get the result that you want. So I'm going to multiply again. Right now I have meters per hour. Is that what I want? No, I want meters per second. So guess what? I have to do something about these hours. So I'm going to put hours up there, and I'm going to put seconds down there. Now, this only works if you know what the relationship is. And I do. I know that 1 hour, well, do you guys know this? If you don't know how many seconds in an hour, it's 3,600. Yes, very good. It's 60 times 60. Now, if you didn't know that, you could go hours to minutes and then minutes to seconds. You just keep multiplying by all these conversion factors. So I know this, so I can do this. So guess what? Hours and hours cancel. I'm left with meters per second, and that's exactly what I want. So now what you do finally is you say, what numbers do I have left over? I have 100 here, and I have to multiply by 1,000 here, and I have to multiply by 1 on top. So 100 times 1,000 on top. And on the bottom I have, well, this was a 1 times a 1 times 3,600. So my answer is going to be 100 times 1,000 divided by 3,600. That's going to be meters per second. 2 zeros go with 2 zeros there. 100 times 10 is 1,000 divided by 36. What's 1,000 divided by 36? And you don't have to do that simplification that I did with the zeros. You don't have to do that. Just plug that all into your calculator, and you should get 27.77 meters per second. So we compare these two, and which one is faster? 30 meters per second is faster than 100 kilometers per hour. So when you're driving down the road at 100 kilometers per hour, you're not going as fast as 30 meters per second even, which is kind of weird to think about if you've ever thought about that. Now maybe you will. Okay? So you're actually only going, if you're going 100 kilometers per hour, you're only going 27.77 meters per second. All right? So unit analysis is handy. I tell you that in science, in Physical Science 20, when you guys get there, you'll be needing to do unit analysis, and you'll explore it more as you go forward in math. Okay, so that's all for 8.1 homework I'm going to talk to you about. We need to get into 8.2 here today. All right. See you later.